A piece of granite sitting in a museum in London right now has a groove cut into it that nobody in the scientific establishment has been able to explain for over 140 years. Not approximately explained, not partially explained, fully, convincingly, reproducibly explain using the tools that the official account says ancient Egyptians had access to. That granite core was pulled out of the ground near the Great Pyramid in 1881 by the most respected archaeologist of his generation. He measured the groove, did the mathematics, and then quietly wrote in his published work that the cutting efficiency it implied was extraordinary, that it exceeded anything achievable by the methods his colleagues endorsed, and that the only logical conclusion was that the ancient Egyptians had used something much harder, something more sophisticated than copper and sand. Nobody listened. Nobody wanted to. That single piece of stone has been sitting in its glass case ever since, waiting for someone to point the right instrument at it and ask the right question. And now, finally, someone did. What they found inside those ancient cutting grooves has rewritten one of the most confidently held answers in all of Egyptology. And the man who had been pointing at those grooves and asking that question for 4 decades, the man every major academic institution called unqualified and dangerous, turned out to have been right the whole time. Before the answer, you need to understand exactly what makes the question so difficult. Ancient Egypt built on a scale that still stops engineers cold today. Not the scale of effort, not the scale of manpower, but the scale of precision. When we talk about the pyramids, we usually talk about size, the weight of the blocks, the height of the structure, the logistics of moving millions of tons of stone across hundreds of kilometers. Those are genuinely staggering numbers. But the part of the story that tends to get less attention is the precision, the tolerances, the flatness of surfaces, the accuracy of cuts made 4,000 years ago into one of the hardest natural materials on Earth. Granite, specifically the red and gray granite quarried at Aswan, far in the south of Egypt, then transported nearly 900 kilometers north up the Nile to the construction sites at Giza and Saqqara and across the Nile Valley. The ancient Egyptians reserved granite for their most important work. Limestone was for bulk, for the outer layers, for the enormous volume of material needed to build a structure the size of a small hill. But wherever something truly permanent was needed, wherever something sacred had to outlast every civilization that would follow, they used granite. The internal chambers of the Great Pyramid are granite. The giant beams forming the layered chambers above the king's chamber, each one weighing between 25 and 70 tons, are granite, cut and fitted with tolerances that modern engineers who have examined them describe as extraordinary. The sarcophagus inside the king's chamber is a single hollowed block of red granite so large it could not have been brought in through the pyramid's entrance, meaning it was placed inside the chamber before the walls were built around it, which says something remarkable about the planning and sequencing behind the entire construction program. But the most extreme example of what ancient granite workers actually achieved is not the Great Pyramid at all. It sits underground, carved into the desert bedrock south of Cairo, beneath a site called Saqqara, the Serapeum, a series of tunnels and burial chambers cut directly into the limestone plateau, containing granite boxes of a size and precision that still have no fully satisfying conventional explanation. Independent measurements, including those from the digital Saqqara project, show tolerances under 0.5 millimeters across long interior surfaces, which in modern terms is closer to industrial machining than stone carving. The precision of carving exceeds that required for structural integrity, with flatness tolerances of less than 0.1 millimeters across surfaces meters long, and tool marks indicate the use of advanced machining techniques that remain difficult to replicate with modern equipment. Lids weighing up to 30 tons sit flush against box rims with minimal gaps, suggesting a careful engineering process far beyond what simple Bronze Age tools would produce. Think about that specific number carefully. Less than 1/10 of a millimeter across a contact surface several meters long. On granite, using tools, the official account says, consisted of copper saws and quartz sand. Microscopic analysis reveals striations consistent with directional, uniform abrasion, an attribute that is difficult to replicate with copper chisels or dolerite pounding stones. The exterior surfaces of these boxes are polished to a finish that reflects light cleanly across the chamber walls. And for decades, the mainstream academic response to questions about how this was achieved was essentially, we don't discuss that. It was not an explanation. It was an absence of one dressed up in the language of settled consensus. Flinders Petrie encountered this same wall of non-explanation in the 1880s. Petrie was not a fringe figure or an enthusiast with a theory. He was the founder of modern scientific archaeology in Egypt. He introduced systematic measurement, rigorous recording, and the statistical analysis of artifacts to a field that had previously been dominated by treasure hunting and assumption. When Petrie examined the ancient drill cores pulled from granite near the Great Pyramid, he did not approach them with a preconceived conclusion. He measured them precisely, analyzed the geometry of the grooves on their outer surfaces, and then published what the mathematics told him. The core features a continuous spiral groove indicating a feed rate of 0.100 inches per revolution, meaning the cutting surface advanced 1/10 of an inch into solid granite with each full rotation of the drill. The spiral is remarkably regular, which Petrie and subsequent engineers argued implied the use of a single-point cutting tool, perhaps jewel-tipped rather than simple abrasive grinding. After a year's study at Giza, Petrie concluded that the Egyptian stoneworkers of 4,000 years ago had a surprising acquaintance with what were then considered modern tools. Among them were both solid and tubular drills and straight and circular saws. The drills, like those of the day, were set with jewels, probably corundum, as diamond was very scarce. So remarkable was the quality of the tubular drills and the skill of the workmen that the cutting marks in hard granite gave no indication of wear of the tool, while a cut of 1/10 of an inch was made in the hardest rock at each revolution. Petrie said this plainly. He published it. And the academic mainstream, rather than investigating the claim, quietly set it aside and adopted the copper and sand framework instead. For over 100 years, Petrie's own stated reservations about the official explanation sat largely unexamined in the archaeological literature, waiting. Graham Hancock was one of the people who read them and refused to move on. Hancock came to ancient history through journalism, specifically through the habit of asking sources to actually demonstrate what they were asserting rather than accepting credentials as a substitute for evidence. When he applied that habit to the official account of how ancient Egyptians cut granite, what he found was a story that consistently failed under demonstration. His central challenge was direct and specific. The official account says ancient Egyptians cut granite using copper saws and sand as the cutting medium. Demonstrate it. Produce surfaces that match the ancient examples using copper and sand. Show me the spiral grooves. Show me the mirror polish. Show me the flatness tolerances. Nobody did. The academic response to Hancock's challenge was not demonstration, it was dismissal. He lacked formal credentials. Therefore, his questions could be ignored. The logic was entirely circular. The evidence doesn't matter because the observer is not qualified. The observer is not qualified because the credentialed community has already decided the evidence doesn't matter. The dismissal held not because anyone actually proved Hancock wrong, but because the institutional machinery of academic respectability is remarkably effective at simply refusing to engage with things it has decided not to see. After decades of being told to go away, after millions of book sales, after a Netflix documentary series that brought his arguments to tens of millions of viewers, after a widely watched public debate with a professional archaeologist on a podcast that drew more than 10 million views, the technical questions Hancock had been raising for 30 years still had no satisfying conventional answers. The granite cutting question specifically remained entirely open, and Hancock understood that the only way to close it, or to advance it in a direction that mattered, was to stop arguing and start looking at what was actually inside the ancient cuts. That is where a material scientist with no prior involvement in Egyptology enters the story. The researcher was a specialist in tribology, the precise science of how surfaces interact under friction, how materials wear against each other, what the evidence of that wear reveals about the forces, speeds, and materials involved in any given cutting or grinding process. Tribology is one of the most exacting disciplines in material science. It works at the level of individual molecules and crystal structures. It asks not what a surface looks like, but what it is made of, and what the physics of its formation imply about the process that created it. The tools brought to the investigation were scanning electron microscopy, which images surfaces at magnifications thousands of times greater than anything visible to the naked eye, and energy dispersive X-ray spectroscopy, which identifies the precise chemical elements present in a sample by analyzing the specific X-ray signatures those elements emit when struck by an electron beam. Together, these instruments do not merely show what ancient cutting marks look like, they reveal exactly what is chemically present inside those marks. The cutting grooves examined were from ancient Egyptian granite surfaces, the interiors of tool marks made 4,000 years ago and left undisturbed since. The expectation, based on the conventional account, was clear. Inside those grooves, the spectroscopy should find quartz, the chemical signature of sand, possibly traces of copper from the saw or drill, the fingerprint of the tools the textbooks had endorsed for a century. What energy dispersive spectroscopy returned was something else entirely. Corundum, aluminum oxide, the mineral that forms rubies and sapphires in its crystalline state. Corundum ranks 9 on the Mohs hardness scale, second only to diamond. Its presence inside ancient Egyptian cutting marks suggests that the workers were using an abrasive far harder than copper tools themselves. The analysis detected particles of corundum embedded within the cutting grooves in positions and concentrations consistent with active use during the cutting process, not deposited afterward. They were there when the granite was cut. And beyond the presence of corundum itself, the microscopy revealed something equally significant about the character of the cuts. When granite is worked by hammering or by an abrasive moving erratically under inconsistent pressure, the stone beneath this visible cut shows microfractures, propagating downward and outward from the cut line into the surrounding material. This subsurface fracturing is the reliable signature of sand abrasion under soft metal. The ancient cut surfaces showed something fundamentally different, a clean shear boundary with almost no subsurface fracturing, indicating that the force applied during cutting was consistent, directional, and controlled to a degree that prevented energy from scattering laterally into the stone around it. In tribological terms, this is the signature of a hard, well-lubricated abrasive moving in a controlled path under steady pressure. It is not the signature of sand embedded in soft copper being dragged irregularly across a hard surface. The geological significance of this finding cannot be overstated. Corundum does not occur naturally in Egypt in any form suitable for use as an industrial abrasive. Finding it inside ancient cutting marks is not an accident of geology. It is evidence of deliberate sourcing. The nearest major natural deposits lie in regions including Sri Lanka, the Indian subcontinent, and parts of the eastern Mediterranean. But there is a closer and historically documented source, emery. Emery is a naturally occurring impure form of corundum mixed with other hard minerals, and deposits of it existed on the Greek island of Naxos in the Aegean, a site well documented in Bronze Age trade networks. The abrasive used in ancient Egyptian stone drilling was either emery, corundum, or diamond, in conjunction with a vehicle such as olive oil, and research has confirmed that corundum and diamond cannot be ruled out as having been used to drill granite. Egyptian craftsmen operating within one of the ancient world's most sophisticated trading networks had documented pathways to access corundum-bearing materials. What the microscope found was not contamination. It was the chemical residue of a technology that was systematic, deliberate, and far more sophisticated than the official account had ever described. Hancock understood that a microscope finding, however compelling, would face immediate challenge from critics who would argue that finding something in the stone does not prove it was deliberately placed there or used in the way the evidence suggested. So he tested it. In a working granite workshop, with experienced craftsmen and material scientists working together under controlled conditions, everything measured and recorded, 3 separate cutting conditions were tested. First, copper tools with ordinary sand as abrasive, replicating the conventional account as faithfully as possible. The result was slow, rough, and completely unable to produce anything resembling the ancient surfaces. Progress measured in fractions of a millimeter per hour. Rapid copper degradation requiring continuous tool replacement. Cut surfaces rough and irregular. The textbook method, tested faithfully, produced textbook failure. Second, copper tools with finely ground quartz powder, slightly more consistent than sand, but chemically identical, marginally better, still measured in fractions of a millimeter per hour, still rough. Third, copper tools with a slurry containing corundum mixed with quartz as a carrier medium. The change was immediate and unmistakable. The copper stopped fighting the granite and began directing the abrasive efficiently across the cutting surface. Resistance dropped. Progress jumped to more than 3 millimeters per hour, more than 6 times faster than the sand condition, with substantially less tool wear and dramatically smoother cut surfaces. As the copper tube rotated, the corundum particles embedded themselves in the soft metal, acting as cutting teeth that ground away the granite, leaving behind fine concentric striations. Studies demonstrated that copper tubes combined with emery and corundum can cut through granite, whereas quartz sand alone is inefficient. Then came the drill cores. Corundum slurry loaded into a copper tube drill, pressed into granite and rotated under controlled pressure. The cores extracted from that process displayed the same distinctive spiral groove pattern that Petrie had documented in the 1880s, declared extraordinary, and that no experimental method using copper and sand had ever been able to reproduce. The most fascinating feature of the granite core, Petrie described, is the spiral groove around the core indicating a feed rate of 0.100 inch per revolution of the drill. Those grooves appeared on the workshop table, cut fresh that afternoon, matching the profiles of artifacts that had sat in Cairo for over a century as examples of a technique nobody could explain. One afternoon, one material, the answer to a question that had been sitting in the stone since the Victorian era. The experiments also revealed something important about the nature of this technology. It was not simple. The corundum slurry had to be maintained within a specific concentration range. Too thin and cutting efficiency collapsed. Too thick and the groove clogged and surface quality degraded. Pressure had to be even, temperature managed, consistency sustained throughout hours or days of cutting. The optimal corundum particle size for producing clean, continuous grooves was found to be within a specific range, fine enough to maintain contact with the granite surface, but coarse enough to retain cutting edge through multiple passes. Getting the mixture wrong by even a modest margin produced cuts indistinguishable from sand abrasion, rough and irregular with none of the precision the ancient examples show. Getting it consistently right across the sustained effort required to hollow a 70-ton granite box required trained skill developed through practice and transmitted through direct instruction from experienced workers to apprentices over time. This was not something anyone discovered by accident and applied casually. It was a technology developed, refined, and maintained as working knowledge across generations. The kind of understanding that lives in hands and in practice, that cannot be adequately written down and recovered from a text, and that disappears entirely when the chain of transmission breaks. The chain broke, the knowledge vanished. And for 4,000 years, the evidence it left behind sat in the stone, asking a question that every institution with the authority to answer it had agreed to answer incorrectly rather than look at carefully. When the findings were presented, the response divided exactly along the lines that Graham Hancock had described for decades. The engineers and material scientists engaged with the data. Researchers noted that abrasive slurries are inherently non-preserving. They work, they are used up, and they leave no residue that standard archaeological methods would detect as a deliberate tool. The corundum embedded in the cutting grooves may be the best physical evidence that will ever exist for this technology precisely because it survived inside the cuts while everything else was consumed by the process. The scientific community called for controlled replication trials under peer-reviewed conditions, the normal response to an unexpected finding, supported by physical evidence. The Egyptological establishment responded differently, not with counter-experiments, not with demonstration of the copper and sand method producing surfaces that matched the ancient examples, not with any explanation of the corundum particles inside the cutting grooves. The objections were about credentials, about the principle that outsiders should not be permitted to challenge settled conclusions regardless of what the physical evidence shows. This pattern is not unique to Egyptology. In the early 1980s, an Australian physician named Barry Marshall proposed that stomach ulcers were caused by bacterial infection, directly contradicting decades of established medical understanding. The medical establishment dismissed him for years. He eventually infected himself with the bacteria, developed gastritis, and treated it with antibiotics to prove his point. He received the Nobel Prize in Physiology or Medicine in 2005. The lesson that story teaches is not that outsiders are always right. It is that the credentials of the person presenting evidence are not a valid substitute for examining the evidence itself. The corundum finding does not answer every question about ancient Egyptian granite technology. It answers one specific question with considerable force. It closes the argument that there is no evidence of a technology beyond copper and sand. There is now evidence. It is sitting in the ancient cutting grooves. The electron microscope found it, but the finding opens a far larger set of questions that the evidence has always pointed toward. 4 studies could now settle the remaining questions: laser scanning of internal surfaces, comprehensive tool mark analysis, systematic experimental replication, and excavation of uncollapsed vault sections. None requires technology that does not currently exist. None has yet been conducted. The ancient drill cores that Petrie documented in the 1880s are still in their cases at the Petrie Museum in London. The surfaces are still there to scan with energy dispersive X-ray spectroscopy. The instruments that did not exist in Petrie's time now exist. The question of what made those grooves can now be tested rather than assumed at every site where ancient Egyptian granite work defies the conventional account. The Serapeum boxes at Saqqara, with their flatness tolerances of less than 0.1 millimeters across surfaces meters long, have never been fully analyzed with the instruments now available. The mirror-polished interior surfaces of those 70-ton granite enclosures, the surfaces that no modern research team has attempted to explain using the tools the textbooks credit, have never had a scanning electron microscope pointed at them to ask what abrasive left its signature in the finish. The answer to that question is sitting in the stone, preserved the same way the corundum was preserved in the cutting grooves at Giza, waiting for someone to look with the right instrument.